All right, so in this video, I'm gonna be explaining another important paper, but this time for large scale graphs, for very large graphs. And it is written by people in Helmholtz Institute. And so their approach is based on random walk. And they say here, this paper in 2025, in this journal, this Transactional Machine Learning, TMLR. So they said that previous diffusion-based graph generation methods have shown promising results, but they often struggle to scale to large graphs. The approach of this paper is good if you don't have a label for nodes and edge. For example, in molecule generation, you have atoms, different atoms, carbons, nitrogen, oxygen for node labels, and you have edge type, different kind of bonds like single bond, double bond. But they completely, if you just use a random walk, it depends on what kind of random walk you're using. But they use the default version of that, and so it ignores the information, the attributes of the nodes and the edges. So their method is very simple, but it's not practical for molecule generation when you care about node labels and edge labels. So their benchmark is those large, for example, social media data sets, large graphs, and so they propose this arrow diff, which is autoregressive random walk diffusion. So as you see, the diffusion model, you have just the initial graph, just random nodes, 1, 5, 6, 2, 4, but it's in 1 to 6. And then the generation, you care about a random walk. From random walk, you generate, via this edge proposal, you generate gradually, you generate a graph. Then now, from this sample, you sample start nodes and repeat. Because depending on your start node, now if I say my start node is 5, then I repeat, it may become 5, 1, 4, 6. So that's why you are learning the random walk and also edge proposal to find the edge probabilities to construct the G and the next iteration. So the bottleneck is not the bottleneck. I mean, the cons of this approach is it doesn't care about the node labels and edge labels. As you see, it's just a default random walk. So they set a background on order agnostic. We call it any order. For example, we have any order diffusion models. You don't care about, it's not autoregressive. It can be anywhere. It's a set-oriented mindset. And the random walk diffusion, they just maximize the log likelihood. So given the previous things that has happened, what is the next step that we should go? And so it is outlined in algorithm number 2. So we have the input is a trained OA ARDM. We have a trained graph neural network. And the output is this generated graph. So we start with the empty graph, set the initial nodes to all nodes in the graphs, because you can start from any node. Then for L steps, let's say L time step, we sample one random walk for each start node. Compute edge proposal, and when you have a lot of proposals, we run the GNN to obtain the probability of all edges. Union of that with the edge proposals that you have obtained in step number 7. Then you sample the valid one, because many of these are not valid edges according to edge probabilities. So edge update, then if L is less than L, we compute the node degree. We compute the node degree. We compute D, and using that we compute probability of each node. Then you sample, start nodes. So it's pretty simple algorithm. And for optimizing the random walk, we sample the t, we sample sigma. If it's less than t, we compute m, we compute I, and from this we compute L. Then this loss can be written. So the data set, as I said, they just used big, very large data graphs, because they claim that their method is good for large graphs. So they look at CiteSeer, Quora, PubMed, and their results is here for different data sets like CiteSeer. They compared for different models like NetGAN. I will explain it in a different video, NetGAN, with variational graph autoencoder, compare it with ArrowDiff, which is their model. Here it is the graph generation results of NetGAN, VGAE, Edge, Graph RNN. I think they have drawn inspiration from NetGAN. So these are figure 6 provides visualization of training split of synthetic SBM, stochastic block model graph, as well as generated graphs. So this is that we observe that it is able to capture these community structures when you look at the original graph.